Okay, practice for the CLEP calculus exam. I have two different ones, official CLEP practice things that I found on the internet. Here are the URLs. I try to remember to link them in the description. So we'll just start off here, get going with it. Question number 1, if y equals all of that, then dy over dx, which just means the first derivative, the derivative of that equals what? So take this, and the question is x plus 1 times x minus 1 times x plus 5. So you multiply them one at a time. X plus 1 times x minus 1 is, of course, x squared minus 1 squared, which is just 1, multiplied by x plus 5. So then you do your regular FOIL stuff. X squared times x equals x cubed plus x 5 x squared minus 1 times x is x minus 5. So you take the first derivative using the power rule. So you take the exponent, move it out in front, and subtract 1. So x cubed becomes 3x squared plus x squared. Move the 2 with the 5. 2 times 5 is 10 times x to the first, 2 minus 1, x to the first power, minus x. So you have x to the first power, 1 comes down, 1 minus 1 is 0, so the x goes away, and then the 5 doesn't have an x, so that whole thing just goes away. And so you're left with that answer, which is C right there. So the next problem here, at which of the 5 points on the graph in the figure above are dy over dx, meaning the first derivative, and d squared y over dx squared, meaning the second derivative, both negative? Where are they both negative? So let's discuss some conceptual things here. If you have a graph, and the graph has a positive slope, that's the initial graph, then the first derivative, which represents the slope, will be positive. And of course, if you have a graph and the slope is negative, then the first derivative will be negative. But it actually, repeats as well. It follows up. If the first derivative has a positive slope, then the second derivative represents the slope of that. So the second derivative will be positive. And also, if the first derivative has a downward slope, it's decreasing, then the second derivative will have a negative value. But what does this mean to our original function then? If the slope is increasing or the slope is decreasing, it means as you increase your value of x, that you're getting a bigger slope or a larger slope. So what do we mean by that? Well, here is your slope is 0. That's more slope, that's more slope, that's more slope. So going that way is an increasing slope. And that's lower slope, lower slope, lower slope. Going that way is a decreasing slope. So if you have an increasing slope, you're going from something that's going down like this, and as you're going across greater x values, the slope increases as you go. So an increasing slope, you might get something like that. And by the same aspect, if you have a decreasing slope, you might start with some kind of higher slope, and then as you go along, the slope gets lower, the slope gets lower, slope gets lower. So you're going to have something like this. And so we call these concave up and concave down. But what you're really looking at is, as the slope changes, the first derivative of the slope reflects how the slope is changing. And then the second derivative tells you how quickly the change in the slope is changing. So let's take that back to our problem here. So where is all the points where the first derivative, the slope, is decreasing? So everything where the function is headed downwards. So we have a decreasing or a negative first derivative in that area, and an increasing or positive first derivative there, and over here, and around D it goes flat, so that looks like it has a slope of about 0. And then we say, where is it concave up and where is it concave down? So we have a concave down here to somewhere around right there. So the second derivative is negative there because the slope is decreasing, and then the slope picks up and starts increasing again. So the second derivative is going to be positive there. So where do we both have a negative slope and concave down? That is going to be at B. So we're at B. So now the third problem. Which of the following is an equation of the line tangent to the graph of f of x equals x cubed minus x at the point where x equals 2? And f of x is just a fancy way of saying y equals. So we're asking about the line tangent to the graph, meaning the line that has the slope, and we find the slope with the first derivative. So we have f of x equals x cubed minus x. So the first derivative, f prime is another way of saying the first derivative. Playing the power rule, move the 3 to the front and subtract 1. And then it's already 1, so you move the 1 down and the x goes away. So this is the equation of the first derivative, and we want to know what is that where f is 2. So we're going to fill in there. 3 times 4 makes 12, makes 11, obviously. So the slope of the line tangent to the graph at x equals 2 is 11. We go back here, and there's only one option where the slope is 11. That's D. And the 6 and the 2 just comes out of x equals 2, and the point at that tangent, y equals 2/3 minus 2 equals 6. That's where the y equals 6 comes from. But because the slope was 11, that it's going to be the D. So here, number 4, we have an integral e to the x plus e dx equals what? So we have e to the x plus e dx. So e to the x is one of those special integrals or one of those special derivatives where it just equals itself. So, the derivative of e to the x equals itself, so the integral of e to the x also equals itself. Now here, the e is by itself, so it's just a constant like any other number, like if it was a 4 or a 5 or a 10, it's just a number by itself. And so when you integrate that, you're doing the reverse of a derivative, so it's just multiplied by an x, because if you were taking the derivative of that, 1 comes out in front, the x goes away, and you're left with e. So e by itself, it's just a constant number, becomes e to the x like any other number would. And then with any indefinite integral, you have to add the c for some unknown constant that might be there. And we look at our options here, and that is indeed selection B. Here's number 5. And they give us this function, x over 1 plus x squared. They show it out here, and we can see that it looks like it's heading towards the x-axis asymptotically as it goes further out. And it's asking us which of these following statements is true. So now we have some limit questions. And the first statement is saying, what value is it approaching as you go out to plus infinity and negative infinity? And, we can kind of figure from the equation, if you plug in infinity over 1 plus infinity squared, well, the 1 is pretty insignificant compared to infinity, so that goes away, and you have infinity over infinity squared, so you can kind of get rid of that and get rid of the squared. So you're left with 1 over infinity, which is essentially going to be 0. So that proves what I said before. It's approaching 0 asymptotically, and this is coming down to 0 from the top, and this is coming up to 0 from the bottom, but they're still both going to 0. So regardless of negative infinity that way, positive infinity that way, they're both going to be 0. So we think this is true. So the next one asks, as it approaches 0 from the negative direction or from the left, is that the same as the value at 0 approaching from the positive direction or from the right? And this one is fairly easy for this question because it's actually continuous there. It actually has a value at x equals 0. It is just 0, regardless of which direction you come at it from. So that is also true. And the next one is asking, if you take this, subtract a half, and divide it by x minus 1, it's suggesting that the limit as x approaches 1 does not exist. So what's happening here? Well, you're subtracting a half, which just kind of shifts it down a little bit. And then you're subtracting or dividing by x minus 1. So that's kind of going to distort it a little bit. But then the special thing happens at x equals 1. Now at that point, you're going to be dividing by 0. 1 minus 1 equals 0. So at that point, you're going to have a little hole in the graph because you have a divide by 0 error. But so the question becomes, the rest of the graph on either side, as it's coming towards x equals 1, does that exist or does that not exist? So and basically it does, because just because you're dividing by a number, it leaves the rest of it intact, and so that limit will exist. And there's only a few circumstances where a limit is not going to exist. If there's a mismatch on either side of the limit, But here you're starting with a continuous function. And then so just because you take a chop out of it at x equals 1 does not stop it from having that nice flow that it already had. So we're going to say that limit does exist. So the statement that it doesn't exist is false. So we're going to say 1 and 2 are true, selection B. And next 5 in the next video.